Now, we can also combine different variations and multiple variables in the same problem. So that's what we're going to focus on in this video, looking at some of those examples. So combined variation is when you have both direct and inverse variation at the same time. And it's typically with different variables. So it's not that it's occurring with the same variable, but it's with different variables in the same problem. So the owners of Rollerblades Plus determine that the monthly sales of their skates vary directly as their budget and inversely as the price. So what's going on here? So we have direct with their budget, which is variable A, and inversely with their price of the skates, which they're calling P. And I don't see anything else. I don't see any squares or cubes or anything weird going on, right? The variables seem normal, but I do have two different kinds of variation. So what's going to happen here is we're looking for sales, which is S. So instead of using Y and X, I'm going to use S is equal to, there's always a K. And then we're directly with the budget. So this is when you multiply. And this is when you divide. Okay, so that's your setup. So it's S equals KA over P. Now we're told that when $60,000 is spent on advertising and the price of the skates is $80, the monthly sales are 12,000 pairs. So when A is equal to 60,000, the price is equal to 80 and sales are equal to 12,000. These all relate. So here we don't have a pair. We have three values that go together, but we can plug these all in so that we can solve for K. So I have 12,000 equals K times 60,000 all over 80. So here we're going to go ahead and solve, and there's different ways you can solve. So the first thing I would maybe do is multiply by 80 on both sides. And that's going to go ahead and cancel things out. So let's see, I'm going to have 8 times 12, which is 96. And then I have 1, 2, 3, 4 zeros. 1, 2, 3, 4. And then I can go ahead and divide by 60,000. Okay, so all my zeros are going to cancel here. So I'm really just looking at 96 divided by 6 in this case. And we should be getting 16 there. Let's double check. 96 divided by 6 is 16. So our K is equal to 16. So our actual formula then is going to be S equals 16A over P for price. So that's part A here. That is our equation. Now, part B wants us to take the equation and actually answer a question about it. So determine the monthly sales if the amount of advertising budget is increased to 70,000 now. So we're determining the monthly sales. The advertising budget is increased. It doesn't say anything about the price changing. So we're going to assume that the price is still $80. And then we can go ahead and figure that out. So let's see. Our A is going up to 70,000 and our price is staying at $80. So I'm going to multiply my numerator here first. So let's see, 16 times 70,000. So I have 1,120,000, and I'm going to divide that by 80. And I'm getting sales of 14,000. So we expect sales to be about 14,000 pairs. So we're able to go ahead and kind of combine those two different types of variation within one problem. Because a lot of times our problems are much more complicated than just having one variable. So here's a case where our sales are determined by multiple things, by the price and then also by advertising. So the more we spend on advertising, we do see increased sales, but we also have to balance that with the price of the skates. If the price of the skates go up, then because it's a divided by item, then our sales actually go down overall as well. So we're trying to balance between those two features. I'm going to say, you guys can say hi to my cat and goodbye. She's sitting on my book. So that's going to be our final answer there. All right, one more example here. So kind of another way to combine things. This is called joint variation. And joint variation is variation in which a variable varies directly as the product of two or more variables. So basically, it's just that. So something like y equals kxz. So instead of using the word direct over and over again, instead of saying, oh, it varies directly as x and directly as z, we use the word jointly. Whenever you see jointly, it means that all those variables vary directly. So joint variation plays a critical role. One thing in Isaac Newton's formula for gravitation. So here you do have sort of joint variation here going on with the two masses, for instance, and even with the force of even if with the two masses, excuse me. And then I should say you do have inverse variation going on here with the d, which is the distance between the two objects. So you have both. You actually have combined here as well. But you do have joint because you have more than one variable being multiplied is what we're looking at here. So another example where you have this joint variation is in centrifugal force. So another kind of physics application here. So we're going to call that C. And the centrifugal force of a body moving in a circle varies jointly with the radius of the circular path and the body's mass m, and then it varies inversely with the square of the time t it takes to move about one full circle. So this force is specific to objects moving in a circular motion. So think about something moving around and around and around in a circle. My kids and I were actually at a sort of like indoor playground the other day, and they had an object that you could jump over, and it was moving in a circle. So something like that would have centrifugal force, which is that force kind of pushing outward when you have that circular motion. All right, so let's get this set up. So I see that I have varies jointly. So that's just another way to say directly with two variables, the radius r and the mass. So these are things that get multiplied. And I see that it varies inversely with the square of time. So not just time, but the square of time. So that means t squared here. And remember, that is the stuff that gets divided. And our main variable here is c. So that is like your y. So it's c equals k rm over t squared, right? There's always a k, and then we're multiplying with r and m, and we're dividing with the t squared here. All right, so now we should have some information so we can actually find k. So a 6-gram body moving in a circle with radius 100 centimeters at a rate of 1 revolution in 2 seconds has a centrifugal force of 6,000 dynes. So even if you're not a physics person, and I'm not gonna lie, I'm not a physics person, we can still solve this equation. Even if I really don't know anything about the background or the units or what's going on here, we can still solve this. We can do it. So for instance, we're looking at a 6-gram body. So that's the mass. Our mass is 6. The radius is 100. Okay. We're going in 2 seconds, and we're doing 1 revolution per second here. Let's see. Oh, sorry, 1 revolution in 2 seconds here, excuse me. So that's the time, 2 seconds. So it takes 2 seconds to go 1 revolution. And I'm missing 1. Oh, there it is. 6,000 for my dynes. That is the answer for C, right? The centrifugal force is 6,000. Okay. I will clarify here too. So when you talk about time, if the time it takes to move about 1 full circle, that means 1 revolution. So when you see that word 1 revolution, it's not an additional variable that's being added here. It's just telling you that's how long it takes to go one full time around. So it'd be 2 seconds as the time. All right, so let's plug everything in. 6,000 equals K times 100 times 6 over 2 squared. I'm going to clean this up. So 100 times 6 is 600. So I have 600K over 4. And then what I can do is different ways to solve, but I can multiply by 4 first. Kind of cancel out that fraction. So I have 24,000. And then I go ahead and divide both sides by 600. So I have 240 divided by 600. So I'm looking at my K value of 40 here. So my formula becomes C equals 40 RM over T squared. So just going back to that original problem and filling in with my 40. So we're going to have a question to answer. We're going to find the centrifugal force of an 18-gram body. So now we want a mass of 18 moving in a circle, still with radius 100. And this time at a rate of 1 revolution in 3 seconds. So again, the 1 revolution is just how long it takes to go around. The time there would be 3. That's the number that I need. So I'm looking to find C. Radius is 100. My mass here is 18. And then my time is 3. So 3 squared. All right, so let's see. 40 times 100 is going to be 4,000. And then multiply that by 18, and I get 72,000. And I'm just using my calculator here. 3 squared is 9, and when I divide that by 9, I have 8,000. So my answer here is going to be 8,000. And again, go back to your units. So our units here are dimes. So 8,000 dimes. So being mathematicians, we often work in many different fields, right? We have seen business applications, you can see science applications. Here we have a physics application, et cetera, et cetera. Obviously, that's one field of science. A lot of applications in biology and things like that too, and really all over. So for our purposes, as you're going through the homework, don't let the units throw you off. Don't let them intimidate you, or the fact that, hey, I may not know a lot about this topic, right? Maybe I don't know a lot about business problems like the last example we did with the roller skates. Or maybe I don't know a lot about physics, or maybe I don't know a lot about biology, whatever it is that we're doing. But you can still set these up. You can use those keywords. Look for a direct variation or inverse variation to help you set up. Make sure your variables are either just regular variables, or do they have a square or something different going on? And then there should be enough information there for you to plug in and find that K. So you're not going to see like trick examples that are going to not give you enough information. So you should have enough information to find your equation. And then if you have an additional question to answer, you can now use that equation to answer that question.